Okay, hello everybody. Welcome to our Protecting Soil Resource from Degradation Contamination breakout session. And our first speaker is Nicholas Lahu. He's a senior lecturer at Lincoln University. And Dr. Nicholas is going to talk about the absorption behavior of 3 cadmium isotopes in 3 unique New Zealand soils.
Good afternoon. My name is Dr. Nick Lato, and I'm presenting today on behalf of my former PhD student, Darshika Welikala, my collaborators at University of Waikato, Dr. Adam Hartland and Amanda French, and Professor Brett Robinson from the University of Canterbury. And I'm going to talk about the absorption kinetics of different cadmium isotopes in some New Zealand soils. So historic phosphate fertilizer applications in New Zealand agricultural soils has resulted in the accumulation of the trace element in many of these soils. So cadmium is a naturally occurring impurity in rock phosphate products, and as a result, when you use lots of phosphate fertilizers, quite often you get a buildup of cadmium in those soils as a result. But recently there's been some concern that some of that cadmium might be moving out of the soils and leaching into places like the groundwater and maybe even the surface waters. And we really want to have an idea of how much of that is moving into those compartments and where those potential sources are. And that's where stable isotopes come in. They're a very powerful tool that can be used to identify where cadmium found in the various environmental compartments has come from. And cadmium, we're lucky enough to have 7 stable isotopes that we can use to help with this process. An example of this is Salmanzadeh et al. In 2017 looked at the isotopic signature of cadmium in the Winchmore field trial, and they found that archive soil samples up until about 2000 had a very similar cadmium isotope signature to the rock phosphate from the Nauru Islands, and which agrees with the source of the fertilizer being used at the time. And that was very different to the signature that was post-2000s, indicated by those grey boxes there. That was very different from the fertilizer that was used post-2000, and also what's seen in the background soil. So the signature can be used to identify where that cadmium came from. Cadmium generally is more soluble in soils than other trace elements. It's not hugely very soluble, but it's still more soluble than other trace elements, such as lead or arsenic maybe. And the key factors that govern its mobility are the rate of water movement in the soil, but also how the cadmium partitions into solid phase species. So things like precipitation and dissolution, and sorption and desorption, because these solid phase species themselves are not generally too mobile. And then there's also uptake by biota, so when it's taken up in large quantities, it doesn't really move around that much. But then there's differences between isotopes, and these are quite well recognized for things like carbon-12 and carbon-13, that you get this fractionation occurring between isotopes as a result of these processes. In cadmium, between the lightest isotope 108 and the heaviest isotope 116, there's about an 8% mass difference. So there's a reasonable assumption to be made that maybe some of these processes affect the fractionation. And this is something we need to know about, because that can influence the extent to which we can analyze the isotopic signature between different compartments, if it's a process that we need to be recognizing. So the aim of this study was to examine the differences in the sorption characteristics of different cadmium isotopes, looking at the size of the labile pools of these 3 isotopes, 108, 112, and 116, to see if there's any differences between them, and then look at whether the desorption rate constants for these different isotopes vary. So the technique we use for measuring these sorption characteristics is known as DGT, or diffusive gradients in thin films. The technique works by measuring the diffusive flux of solute from the soil into what is known as a resin layer, and this flux is regulated by a diffusion layer of a known thickness and a filter membrane. This the flux, or the supply of solute to the probe, is determined by the rate at which it diffuses from the soil, and as concentrations get depleted, you get a resupply from the solid phase that buffers those concentrations. So those two combinations inform the DGT. As you deploy for longer, you get a greater depletion at the probe interface, and that in turn affects the flux of material into the DGT and consequently the DGT itself. So therefore, the CDGT is dependent on the amount of time that you deploy the probe for. We can use that relationship of the CDGT to the pore water concentration that's measured independently to estimate an index called R. And that R changes with time as well. And depending on the extent to which that R changes, we can make an estimate about the extent to which the solid phases resupply solute to the pore water and then to the DGT. So when the R doesn't change much, we have very strong buffering by the solid phases. But when it changes a lot, it means that we're dealing with a case where most of the supply is mainly through diffusion. Some of the advantages of using DGT is that it doesn't really disturb the soil very much. It works at around field capacity, unlike many extraction techniques where you have a ratio of 1 to 10 or maybe 1 to 50 or 1 to 30 of solid to solution. The processes that are fairly well defined, so it's fairly easy to model and to interrogate those processes. It gives you a fairly clean analytical matrix to work with, and if you're interested in plant uptake, you can also mimic the plant root, but that's not really relevant here. So our experiment consisted of collecting 3 topsoils from the North and South Island of New Zealand, a recent, a clay, and an allophanic soil. We spiked them using cadmium isotopes 108 and 116 to increase their concentration by 0.66 milligrams per kilogram, and then we also added some cadmium at its natural abundance. We lined the soils, and then we equilibrated them for about 5 months at 20 degrees, keeping a constant water content to allow that equilibration to occur optimally. After that equilibration period, the pH had settled at about 6.1 in all soils, and then we measured the extractable KD using a 0.05 molar calcium nitrate extract. We then carried out a time series of DGT deployments where we deployed the DGTs between 4 and 480 hours at a moisture content of 90 to 100% of field capacity. The maximum deployment times were different for the different soils. For Canterbury, we used 480 hours. To Kofire soil, which is a clay soil, we deployed for 384 hours. And the Taranaki soil, we deployed for even less. And the reason for this was the differences in the soil organic matter contents in the soil. Basically, we do not want the soil to go anoxic during the deployment because that can affect dissolution processes and things like that might release cadmium. We're purely interested in the sorption processes. The way the soil was deployed was as a well-defined cylinder contained within a plastic ring above the DGT probe, and above it allowed air to diffuse into the soil, again to prevent those anoxic conditions from occurring. Like I said, the DGT processes, the process that supply DGT in this case, are fairly well defined, so that allowed us to construct a model to model those processes, and that model is called the DGT-induced fluxes in soils, or DIFS model. It considers the binding of the metal by the resin, the diffusion through the diffusion layer and the soil, and also the sorption as a first-order process that's regulated by a desorption and sorption rate constant. And I'm going to be referring to these two variables, the KDL, which is a linear partitioning coefficient between the solution phase and the labile solid phase, so the solid phase that can actually release solute within the duration of the deployment, and also response time, which is an indicator of the speed at which the solid phase responds to that depletion. So very long response time soils, that cadmium wouldn't desorb very quickly from those soils, and that's often reflected by a very low desorption rate constant. So using the way we use DIFS to estimate these two variables is by doing these time series DGT deployments and then plotting them over time as the index R. Then we use the model, modifying the KD and the TC, and to see which values provide the best model fit to those different time series deployments. And by using an error function to represent that fit, we can actually produce these two-dimensional contour plots that show where the error is the lowest between a certain TC and KD combination. So where the solid phase size, so labile solid phase size and the sorption kinetics provide the best representation of the supply of solute to the DGT device. So here are some of our experimental results. So cadmium 108, we did it for the 3 soils, Tekofi, Canterbury and Taranaki, so the allophanic, the recent and the glaze soil. And you can see that the R changes differently for the different soils. So it becomes very depleted in the Taranaki soil, which means that there isn't very much solid phase supply of cadmium to the DGT, while in Tekofi that depletion does occur, but again it's not as dramatic as it is in the Taranaki soil. And there's also some subtle differences between the isotopes, and that contour plot method that I showed you earlier is a quantitative way or systematic way we can use to interrogate these differences. So looking at these results a bit more closely, so putting some numbers instead of graphs, we see some certain patterns emerging. The first one is that the DGT DIFS estimated KDL is higher in all cases than for the extractable KD measured using the calcium nitrate extraction, which suggests that the DGT over these long time periods is sampling a different pool of labile cadmium to the calcium nitrate. The KDL increases for all isotopes in the order Taranaki, Canterbury, Tekofi, so it's lowest in the Taranaki soil, which had the highest organic matter content, and highest in the Tekofi soil. So that high organic matter content may actually be binding that cadmium very strongly, which means that the labile pool is very small. The KDL was highest for the 108 isotope and lowest for the 112 cadmium isotope, which is quite interesting. So there's a definite difference between the 108 and 116 isotopes, but the pattern falls apart with the 112 isotopes in that it's the lowest out of all of them. And this may be because some of these soils had historic cadmium inputs in them. So particularly the Taranaki and Tekofi soil had cadmium concentrations of 0.6 to start off with, and that would have included a fair amount of the 112 isotopes. So possibly that would have aged over time and got bound quite strongly there, and thus the labile pool maybe isn't as big as it is for the other 2 isotopes, which are more fresh. We did equilibrate the soils for 5 months, but it's possible that it wasn't long enough in this case. The cadmium desorption constants, the K-1, which was estimated from the KDL and TCL results, so that's the first order reaction rate constant for desorption, was the lowest in the recent soil and highest in the Tekofi soil. And there's also a fair bit of variation in the desorption rate constant in the Taranaki soil, and this comes from the fact that the labile pool size is very small, as shown by these results. And that causes a lot of uncertainty in the accuracy with which you can estimate the desorption rate constant. It basically stems from the fact that when there's not a lot of material bound onto these labile pools, the effect of the desorption rate constant on the solid solution phase supply is actually relatively unimportant, because it's the total amount that's controlling the desorption rather than the rate constant. But that's something you can read about more if you get into the literature of how this method works. So some general conclusions. So the labile cadmium pool sizes generally vary more between soils than between the isotopes, which is possibly good news if you want to start estimating the uncertainty between looking at, say, for a soil and a groundwater end member, in that it's probably more determined by the soil type than variation between the different isotopes. The general trend of KDL decreasing with atomic weight, but that 112 cadmium is a difficult one to assess, just due to the fact that the spiking results may be unreliable in regards to that, understanding the effect that isotope has. The low KDL in the Taranaki soil may be linked to the high organic matter content in that soil, and possibly abundant iron aluminium oxide minerals, given it's an allophanic soil. It possibly binds the cadmium into non-labile forms that don't get sampled by the DGT to the same extent. And some of the results that we saw with regards to the early stage of the results weren't very well represented by the DIFS model, and it's possible that a two-pool, a model that considers 2 labile pools of cadmium, a fast and a slow one, might yield better representation of these DDT fluxes, especially at the early stages, but that's something that would have to be developed and possibly a project for the future. So with that in mind, I want to thank you for your attention. In that picture you see Darshika, who's the PhD student whose work this was, and myself and Brett Robinson, who are her proud supervisors. This was at her graduation meal. And we also want to acknowledge the contribution that the Minister MB made to funding this project, Madia Salmanzadeh, who provided some really good advice, and also the analytical services team at Lincoln University. Thank you very much, and if you've got any questions, I'd be happy to answer them.
Thank you, Dr. Nicholas, for his informative talk. Sorry, we don't have time for one more question. Let's move to our next speaker, Dr. Shervin Kabiri. She's a postdoc fellow at the University of Ali. It's your time, Shervin. Postdoc fellow at the University of Ali.
Assessing the leaching behavior of the perfluorinated materials from contaminated soil using batch or column experiments, and this work is a part of an ARC project in collaboration with the University of Queensland and CSIRO. In recent years, the mass media's awareness and public people's awareness about the PFAS has increased because of the possible toxicity of these materials. PFAS or perfluorinated alkyl materials, as Mike mentioned this morning, they have been developed from 1940s and they have been used in different applications worldwide. However, the soil contamination with PFAS is always they are related to the firefighting training areas or military bases where the aqueous film-forming foams, which contains high concentration of the PFAS, have been used. And if you look at the Australian PFAS chemical map, you can see that all over Australia there are more than 500 sites that they are contaminated with PFAS, and always the contamination of the groundwater or surface water are originated from these contaminated soils. Oops, sorry. But what are these materials? PFAS, they are a complex and diverse group of the highly fluorinated materials. All of these compounds, they have the same chemical structure. You can see that they have a fluorinated carbon tails, which has a hydrophobic property, and they have different hydrophilic head, which they are the sulfonic acid group, carboxylic, or sulfonamides. But what's the issue with these materials? Carbon-fluorine bond is one of the strongest chemical bonds, and it resists to the degradation. PFAS, they have different charge, but mostly they are negatively charged, and because of having the negative charge, they are very mobile in the environment. And because of their high mobility and their resistance to the bioaccumulation, they can, the resistance to the degradation, they can bioaccumulate in the environment and in the human body. Why we should look at the leaching of the PFAS? Although these materials, they have been developed from 1950s, 40s, but most of the studies related to the PFAS material, they belong to the 10 years ago, or they started to do research from 10 years ago. And they are very short, very few amount of the studies on the leaching of the PFAS, and most of the people, they look at the sorption of the PFAS and the soil and the factor that they can affect their sorption to the soil. It is important to look at the leaching of PFAS from soil because still there are lots of contaminated sites which they contain the legacy contamination, and they can release PFAS to the groundwater or to the surface water. On the other hand, it's very important to determine the desorption of the PFAS from soil because there is still ongoing release of these materials from the source zones, or there is a potential leaching of these materials if they have been disposed in the landfill, or ongoing risk if the soil is treated with the remediation material. In this work, we have collected 12 contaminated soil from different defense sites, and the soil that they were studied they had a different range of the particle size. You can see that they had different sand, silt, and clay percentage. They had the different percentage of the organic carbon and pH. The PFAS of these soils, we just measured the amount of the PFAS that they were in these soils, and the different variety of the PFAS, starting from 4 carbon chain length onto 12 carbon chain length, they were detected in these soils with different functional head group. But PFOS, which is one of the more persistent PFASs, presented at highest concentration in all of the soils. Depending that where we just took the soil, PFAS concentration was different, and it changed from 11.6 to 6.9 multiplied by 10 on the power of the 5 microgram per kilogram. After PFOS, PFHXS was the second most contaminated in these soils. To assess the leaching of PFAS from soils, we used 4 different leaching tests. The first one was the Australian standard leaching procedure, and as you can see that the liquid to solid ratio was 20:1, and the leaching fluid was either alkaline tetraborate buffer or acidic acetate buffer. The second test was multiple extraction. It had the same liquid to solid ratio as the ASLP, but deionized water was used as a leaching fluid, and the number of the extraction was 5 compared to the one in ASLP. We used another leaching test, which is LIF 1313, and the leachate fluid was deionized water, similar to the multiple extraction, but the difference was in the liquid to solid ratio and about the agitating time. And finally, we used the US EPA LIF method 1314, which is a column leaching experiments, and we just monitored the leaching of the PFASs in the column for 9 days. Results. The results of the ASLP leaching test for 12 soil has been summarized here. And you can see that when we have a short chain PFASs, in case of those ones that they have sulfonic acid heads, if the number of the carbon in their chain length was less than 6, there was no difference between their leaching in alkaline or acidic pH. And in case of those ones that they had carboxylic acid head, if the number of the carbon was less than 7, we couldn't see these differences. But when we moved to the longer chain PFASs, by increasing the carbon chain length, their desorption was decreased in acidic pH. On the other hand, what we observed was the effect of the functional head group in these materials. The PFAS that they had carboxylic acid head group, they leached greater than those ones that they had sulfonic acid or they had sulfonamide head group. Although concentration of the PFAS was very high in all of these soils, and it was very high in the leachates, but the percentage of the leached PFAS compared to the total PFAS in the soil was very low, and it means that this chemical was very resistant to desorption. In multiple extraction procedure, what we observed was that short-chain PFASs, like PFBS, PFPES, or PFHXS, they just dissolve mostly by first extraction. And these were the long-chain PFASs, they gradually dissolve. And you can see that, again, PFAS was very resistant to desorption. Similar to the results of the ASLP, we saw the effect of the functional head group during the multiple extraction procedure as well, and those ones that they had carboxylic acid head group, they leached greater and faster than those ones that they had sulfonic acid head groups. The result of column experiments was very similar to the multiple extraction. You can see that those ones that they had shorter carbon chain length, they dissolve faster and they reach the higher concentration very quicker than the long chain PFASs. And when we want to compare the different PFASs with the same chain length but with different functional head group, we find that those ones that they had carboxylic acid head group, they just leached quicker than those ones with the sulfonic acid head groups. And another important thing that we observed was that in the lower pore volume, although the concentration of these PFASs, they are far less than PFOS in the soil, but in the lower pore volume, due to their higher water solubility, they just leached, their concentration was greater in the leachate. And this is why most of these short chain PFASs, they have been detected in high concentration in groundwater. Here I'm just comparing the leaching percentage of one of the short chain PFASs with and two long chain PFASs with two different functional head groups in two soils. The soils, as you can see, they have different properties. The soil one is very sandy soil with more than 94% of the sand, while the soil two has 30% of the clay, and its organic carbon is a little bit better than soil one. But what we found that there was no effect of soil property on leaching of the short chain PFASs, and in case of the long chain PFASs, if they had the carboxylic acid head group. But when we look at the leaching of the PFOS, which has the sulfonic acid head groups, we find that it was leached more in the soil with the sand, with the high concentration of the sand compared to the other soils. Another important thing that we find regarding the effect of the soil property was that if the concentration of the PFAS or PFOS was very low in the soil, they leached close to the 100%. In conclusion, we found that the desorption of the PFASs, it depends to their chemical structure. It can be affected with their carbon chain length, and it is related to their functional head group. In case of the short chain PFASs, there was no effect of the leachate's chemistry, pH, or liquid to solid ratio, or soil property. And almost all of them, they have leached using these different leaching tests. There was a good agreement between the results of the batch and column leaching experiments, and we found that the PFAS's chemical structure, they can affect their leaching greater than the soil properties. At the end, I just want to acknowledge all of my colleagues at University of Adelaide, University of Queensland, and CSIRO, and thank you for your attention. Any question? Okay. Yes?
Those short-length PFAS are very mobile in soil. So how come they're still in the soil and not reached out yet? Is it just because it's quite recent contamination, or because there's very little water properly circulating through the soil and the food conditions?
I think one of the reasons that the short chain PFASs are still exist in the soil is that because there are lots of the other precursors, PFAS compounds, that they are changing to these short chain PFASs. It is one of the reasons. Thank you.
Thanks for attending the talk. What I'm going to share with you is really my experience. I'm not a soil physics person, but after we're working on the tailings for a number of years, we suddenly found out physical properties were very important. Can we start the slide? Okay. So my title is really to share the experience, the lessons we learned from ecological engineering tailings into soil for helping rehabilitate hundreds and thousands of hectares of tailings for the mine industry, because conventional approach using topsoil to rehabilitate is very expensive and not sustainable. I do acknowledge my team and also all the founding companies who have provided the money, accumulate the experience of the last 15 years. My talk is pretty simple. So I'm going to talk about three key aspects. One is the importance, in terms of importance of soil physics in soil ecological resilience, especially in this day and age. The climate change will expose the soil either a prolonged flooding of anoxia effects in the tropics and wet tropics, and the drought will expose the topsoil into prolonged dryness, which will convert or speed up the crystallization of the iron and manganese and silica minerals. We all know the amorphous iron, aluminum, manganese, and silica are very important as mineral cements. And through the tailings rehabilitation research and the soil formation research, which yesterday Song Ling, my postdoc, also talked about, we found actually we need a lot of mineral weathering as the engine to drive the development of water-stable aggregation, which is actually the key building units of the soil physics. By going through that experience, I don't have the data yet, but I propose, can we look at the microbial-driven mineral weathering as the engine to rejuvenate, to regenerate soil physics, to restore or rehabilitate soil ecological resilience, buffer against. I mean, I don't think, a lot of you are from probably soil background. I don't know how many of you have been to the vast landscape of tailings. That's what the tailings look like. And this is 1,200 hectare. This is about 1,000 hectare. So, and tailings are minerals. They're not soil. They share some aspect of parent material, if you like. They are very much of mineral abundant, and they are at the same. They are really not soil. They are like cheesecake, black, forest chocolate cake. And with the weathering, you have these layers of oxidation, but most of the physics is finely textured. And traditional approaches using agronomy incorporation try to amend or quickly improve the chemical conditions to grow plants, which is not sustainable, not feasible. The oldest trial I came across in literature is conducted back in 1952 up in Mount Isa. So that's what triggers us to look at mineral weathering. And this is the iron ore tailings. You saw they are very finely structured, compacted. This is the sodic coal tailings. I don't know how you're going to grow any plants because that lack of heterogeneity of porosity and the lack of water-stable aggregation. Without that, Australian plants evolved from the ancient landscape, very clever to develop extensive root system down to very deep to acquire water so they can transpire, cool themselves down in the summer to survive. Without that porosity and water-stable aggregates, they can't do it. As simple as that. And to create physical structures, not just amend something into it, how can we have sustainable water-stable aggregates rather than just bulking it up? That's bogging it up is conventional agronomy approach because we put something in our backyard to grow some vegetables. But here is how can we utilize that mineral rich to start mineral weathering? This is the bauxite residue. I don't know how you're going to grow plants there too. So that's what we propose. How can we start that? Is we need to use micro-initiate bioweathering of target minerals, depends on what you are dealing with. In terms of sulfidic tailings, pyritic mineral weathering, you start to initiate physical, chemical, and biological interaction. So that's what the approach we follow to try to transform the minerals mostly to oxidize or dissolve primary minerals to form abundant secondary mineral gel. We try to create some of other, borrow some of the chemical material terminology we call mineral cement. It's how can we produce enough that to join the particles together so they can form a high specific surface area. This is Songlin presented yesterday that we substantiate this in our iron ore tailings case. The iron ore tailings, the minerals is very smooth, very shiny. How can we activate dissolution through organic acid production in the microbial decomposition of plant biomass? It's very simple philosophy. And then start to co-dissolve the biotite, the iron oxides to form large amount iron oxyhydroxide to coat the mineral particles to create the mineral cement, glue the particles together. And Songlin's work demonstrates this is feasible, and that creates, again, the organo-mineral association to then the plants can survive, the roots can penetrate, and then the roots itself will take on that relay of rhizosphere interaction and modification to drive that production of mineral cements further. And we have, this is the details a little bit in the initiation of microbial decomposition of biomass. You can see the microbial interaction generates organic acid, low the pH, causing the co-dissolution and aggregation. You can see the organic and microbial hyphae growing if you can magnify. That's the start that initiate that engine of aggregation formation. And Songlin went on to the nanoseams. You can demonstrate clearly if you don't have that mineral weathering event, the iron oxides stay as it is. But if you have that microbial-driven mineral transformation and weathering, you have this organo-mineral association start to happen. Okay? So we try to integrate that microbial process into the mineral transformation to produce the mineral cement. I'll bring up the importance of mineral cement compared to organic cement. Organic cement is coming from a lot of labile carbon decomposition and microbial biomass. And we also try to demonstrate the process of mineral weathering in the pyritic tailings. You can see we can use autotrophic pyrite oxidation, and this is no microbial activity. The tailings stay as it is. But with that pyritic oxidation, we can lead to form a large amount of iron silicate gel acting like cement. To imagine it, if you can just break open a concrete, that's more look like. So this glue will start to glue all the particle quartz and other mineral particles together to form the very stable mineral cemented aggregates. Okay, and then the secondary mineral gel on the surfaces also create interface with organic cement or organic matter. So this is what we learn and start to appreciate. The mineral weathering is a very critical engine to initiate the start, the aggregation of soil physics development. And we have another project. We try to examine how can we restore soil physics in the stockpiling topsoil in the in WIPA, in the wet tropics. Any of the soil stockpiling will change the redox status, a gaseous phase, and then we'll shift the microbial community to adapt to more anoxia condition. With that, you can see the organo-mineral association and the physical structure start to degrade. You can see this is with the organic matter added in to maintain it. You can see the heterogeneity of aggregates distribution. With that long-term stockpiling, you add water in to become a lump, the lack of the structure. So that's why a lot of soil in a mine site get destroyed because of long-term storage of and that degradation of soil physics. Because the physics destroy, you can see the microbial activity also decline, especially after 3 years stockpiling is nothing there. So how do you manage? In this case, how do you manage and restore that microbial catalyzed mineral transformation engine, so you can restore that soil ecological resilience? So that's what's triggered me to give this talk. And so we joined the lesson very simple. We borrow the soil formation, and they focus: can we develop a mechanism to examine clay-based soil in either agriculture or forestry or mining after degradation? How can we develop mechanism to restart this mineral transformation so we can rejuvenate the mineral cement and to allow that soil physical structure to persist? Okay, without that, then you do not have soil sustainability. And this is another study we found here. You can see very clearly showing the mirror cement cementing everything together. Based on this evidence and earlier evidence, we're proposing a sort of a model, conceptual model here, is can we restart the pump or the engine of mineral weathering by priming the specific microbial activity to maintain the organic cement. The organic cement is really there at the basis of biological process. The mineral cement is the critical nuclear to maintain the water-stable aggregates, okay? And so what is the, in terms of future, maintain the soil physics and soil ecological resilience? How can we repair intensively cropped or inundated or flooded or prolonged dried crystalline soil by regulating this process? So that's the lesson I learned out of dealing with tailings research. If we can share this lesson in terms of maintaining soil health, soil physics resilience. Thank you very much. Any questions? Good, no question.
Just on the pioneer plants that accelerated some of that, what were they, or a particular group of plants?
Depends on, I mean, the iron ore country, you tend to use a lot of kinopon, like atroplex, because they are always come when you land disturb. And they're very harsh, they can tolerate the heat, the cumulative salt. One of the consequences of accelerated mineral weathering and transformation is they will temporarily release large amount of soluble solute. So the pioneer plants should be able to cope with that. You know, in the coastal area, sodicity, then you're more looking at alkaline and halophyte, alkaline tolerant halophyte.
Thank you, Professor Huang. Our next presenter is Danny from Universitas 11 Maret in Indonesia.
Greetings, hello, my name is Dendra Badadan Tanjung and I am from Universitas 11 Maret, Indonesia, and I'm here to present about my study. It's called Relation Between Restoration of Bengawan Solo Watershed Area with Soil Quality Properties. And we can start now. Bengawan Solo is a river located in Central Java, Indonesia. It is approximately 576 kilometers long and face a rapid erosion and degradation rate. And it is affected by a change of land use at Bengawan Solo watershed area. As we can see at the slide, forest land decreased by 31% and transformed to cultivated land, while settlement land use increased by 26% at Spanish. Despite the the restoration of the land use had been held by government by using agroforestry method. Next, as we look closely at 7 years, most land use changed at Bengawan Solo, impacting swamp and mural ecosystem. And as we can see at the data, the land was converted to open field and rural settlement. Next, next to the methods, it is one sampling. We determine the location sampling by overlay the map, geology map, toposequence map, and soil type map. We're using certified random sampling methods to determine agroforestry treatment site and one control site forest. So we had 9 sites. And the survey we using descriptive explorative using field survey at Watershed Keduang, Bengawan Solo Watershed, Wonogiri, Indonesia. And the analysis that we doing is soil indicator. Most of soil indicator, which is chemical, physical, and biological. Example, it's pH, CEC, availability P, and nitrogen total, potassium availability, CO organic, bulk density, permeability, soil respiration, and carbon biomass. And we also calculate the fauna and flora diversity using TSBF hand sorting by Anderson method in 71 and the monolith method for fauna. And we using transect method for collecting the flora data. And we using percent correlation to determine the minimum data set. For determine and next we determine the scoring soil quality index, and we also calculate the soil deterioration index, and we try to look the most volatile variable that influence the index, each index. This study was needed because it's help to evaluate the impact of the restoration doing by the government of the area to the watershed-based to the soil quality. Next, we try to look at the results. One is the land use and site vegetation. We describe the site 1 as a land use forest. Its vegetation is cycas, fern, and sage. 2. Agroforestry. Vegetation is jackfruit, clove, mahogany, pine, avocado, banana, lemongrass, tobacco, chili, galangal, and bean. 3. Agroforestry. We using clover, Gliricidae, mahogany, papaya, cassava, banana, tobacco, chili, bean, cyperus grass, taro, peanut. 4, land use agroforestry, site 4, we see the vegetation as albizia, mahogany, teak, melicae, cassava, corn, elephant grass, and peanut. Site 5, vegetation is cyperus, pine, cassava, and teak. Site 6, we eat pine, cassava, banana, calapogonium, ferns, taro, elephant grass. Site 7, it is lam toro, teak, cashew, setaria grass, cassava. 8, agroforestry, vegetation is lam toro, corn, cassava, teak, albizia. 9, agroforestry, we look for mango, cassava, banana, teak, peanut, and coconut, which is the most coverage crop coverage. It's in site 2, agroforestry 1, and the lowest coverage in site 4, agroforestry 3. It is 60 till 70%. Next, we look for fauna biodiversity data. As stated in the graph, site 2 had the most richness index, also diversity index. As we know, site 2 was land with the most crop and variety diversification, and surprisingly, site 1 forest and site had the lowest diversity index, also site 9. Next, flora biodiversity is the same that site 2 had the most flora diversity, which is 30 types flora of fauna, 30 types of flora, and supported by the highest value of carbon dioxide at this site, which is the highest. And site 2 also had the lowest score of flora biodiversity. Next, we see the chemical properties. We had 9 variable to look, but as we can see, the site 2 has the most in total. C organic, as carbon per nitrogen index, and organic matter. Next, we move to soil quality properties. We determine that 9 variable, which is soil respiration, microbial biomass carbon, soil depth, aggregate stability, BD bulk density, AWC available water capacity, TOC total of carbon, total organic carbon, pH, and available PTSD. Next, we look for overall scores of SKI. It is the data range assigned 20 until 30. The soil quality index is the average value of the observed variable in each land use, and as we can see, the largest soil quality index is in site 9, which is vegetation is mango, cassava trees, banana, teak, and beans. Next, soil quality index. If we look with the most emphatic value with stepwise regression, it is soil depth. Next, we see for soil deterioration index. We look for the graph. It is almost half of the site we observe. It is currently had soil deterioration sign. It is as we can see at the site, even in the forest, it's site 1, it is site 3, and site 6 and site 8. Show soil deterioration index value. Next, soil deterioration index correlation with soil properties. As we can see with the stepwise regression, it is the most important variable is aggregate stability. Next, the conclusion. As we can see from all the data, it is the land use of all sites had a good soil index. It is range for 20 until 30 score according to Andrew et al. Classification. But research shows several sites that tested was shows the sign of soil deterioration. The index value of the soil deterioration on the forest land is minus 0.76, which is near null. Sign 3 it's minus 2.70. Site 6 is minus 5.26, and the location 8 is minus 4.77. The site 8 had the lowest score, even in SKI and SDI assessment. Next, the acknowledgement. Thanks to Professor Supriyadi for make this study happen, and Dr. Sayatati for the guidance. Thank you.
Thank you, Danny. So we don't have any questions from app, but I got a question actually. Could you explain a little bit about the richness index and diversity index you talk about in your slides? No sound.
It is I again.
Maybe talk into the computer and ask it again. Just talk quite loudly.
Can you hear me, Danny? It's frozen.
Yeah, he's frozen at his end.
You repeat the question again.
Oh, there you go.
Could you explain a little bit about the richness index and diversity index in your slides?
You
Unfortunately, we can't.
Sorry, we can't hear you.
using methods.
Sorry, there we go. Okay. Hold on.
We move to the next one.
So, yeah, that's right. Don't worry about it. You carry on.
Okay, our next presenter is Gauss Forward from the Department for Environment and Water in Australia. So today he's going to talk about monitoring soil erosion risks in the agricultural landscapes of South Australia using satellite data.
Hello, I'm Giles Forward from the South Australian Department for Environment and Water. Together with my colleagues, Tim Herman and Trevor Hobbs, I'm going to present on monitoring soil erosion risk in the agricultural landscapes of South Australia using satellite data. In the South Australian agricultural zone, which is our key area of interest, there's significant areas of agricultural zone that are inherently prone to wind and water erosion due to soil type and texture and topography and rainfall. And the rainfall ranges from about 600 mils used for dryland cropping and pastures down to about 275 millimetres of rainfall. So it's certainly a fair lot of it is sort of the semi-arid category. Historically, soil erosion has been a major issue. More recently, with the adoption of improved land management practices, it's much less of an issue. But things like very dry seasons, bushfires, and climate change certainly are ongoing threats to sustainable use of the land. In South Australia's agricultural zone, erosion risk monitoring has been going on for about 20 years, since year 2000, using field observations at fixed geolocated sites, and the visual scoring primarily looked at combining topography rating, disturbance rating and cover rating, and the cover rating was a combination of cover height, density and percentage cover. More recently, we have been exploring options using Modus fractional cover monthly products developed by Gershman CSIRO. Initially, we looked at this some years ago using a fixed threshold method, but it found it didn't correlate very well with our field observation of cover, surface cover. So a model was developed primarily by Trevor Hobbs that looks at the three indices of bare soil, photosynthetic vegetation and dry vegetation. It does some disaggregation down to 90 metres. There's a calibration against the field survey cover data from geolocated sites for the 4 survey months of the year that the field surveys have been conducted: March, May, June and October. So there's various adjustments and calibrations done in the modelling and a Maxent statistical method, and it also incorporates dominant erosion susceptibility classes as well, for wind and water erosion. So the model, we come up with modelled erosion risk based for the 8 cover rating classes, and also incorporate the soil, inherent soil potential for wind and water erosion to come up with also an actual risk rating. So some of the outputs that we've got from the modelled erosion risk, we can produce maps and data for an individual month of the year for either of the survey months, March, May, June or October, and to really highlights areas of concern that might be marginal or becoming exposed to the risk of erosion. We can do this for each of the survey months of the year, for the October, March, May and June, and start to paint a picture of a time series and a seasonal trend, seasonal changes in erosion risk throughout a year. We can also integrate the 4 survey months data to produce a cumulative measure of risk for the 12-month period, and that's basically the cumulative hectare days at risk divided by the hectares to express just a simple metric as number of days every average hectare is exposed to a risk of erosion. So we're able to do that for every year of the MODIS data. And the time series charts, of course, are also very useful for monitoring the trends and longer-term trends in erosion risk. We can also produce forecast cover risk products based on a current October cover risk data set, where we extrapolate the average cover decline from October to March over a 10-year period, and to come up with a prediction of likely erosion risk in the following autumn in March. And we're also then able to compare that to the actual March and look at the analysis, whether the cover was declining faster or slower than the average, and reasons that might have contributed to that. And some of the other products that we've produced based on the MODIS fractional cover are what we call seasonal conditions assessments, where we derive a plant growth index or a bare soil index from those fractional indices, where we've, for a cumulative period of the year to date, we can plot the anomaly of that cumulative monthly year to date for the current year compared to the 10-year average for that same period. And that shows, for instance, on the left, the red shows areas with significantly lower plant growth and greenness for 2020 compared to average, and the converse for the green areas. And on the right is the corresponding map based on the bare soil index, showing areas that have got barer soil than average, or less bare soil than average. So that, and we can also present these products for more concentrated areas, such as the southern agricultural area or the northern rangelands area of the state, depending on the audience or the people that are going to make use of this information. So they're just some of the examples of what we've been doing. So these products are provided to internal department staff and regional-based landscape South Australia staff to assist them with seasonal strategic and management responses to changing conditions related to erosion risk, and for longer-term monitoring, program planning and evaluation of land management programs. And there's also opportunities for us to further develop these models and refine them as we determine. So that's the main things that I was going to present today. So thank you very much.
Thank you, Giles. Actually, no questions from the app. I got a question. So you mentioned MODIS in your slides. Have you considered like Landsat or Sentinel-1, Sentinel-2 such satellite data? You have to unmute.
Sorry,
Oh,
okay,
thank you.
Can you hear me now?
Yeah, thank you.
Okay, so I think the question was, what about using Landsat or Sentinel imagery? We chose the MODIS as the base data source for this fairly broad-scale monitoring to get to sort of limit the amount of data processing required. If we tried to do that on this scale using a high resolution satellite data set, we would obviously be dealing with a lot more data processing and computing power needed. But so I guess it's a reasonable broad scale tool that we've found, and as I say, the modelling process does disaggregate the 500 pixels down to about 90 metres using sort of Landsat 3 monthly and some other tools. So it gives us a reasonable, sufficient resolution for the sort of district and regional scale monitoring.
Oh yes, so I want to say something more actually. Did you use Google Earth Engine, such cloud platform? Because that's one way to deal with large amount of data. You don't need to download, and you don't need to load the data into some other softwares, just like process in a cloud platform. Have you done that before?
Sorry, I didn't quite catch much of that question. I think it was about other ways to deal with larger amounts of satellite data. I guess, well, I can't, I'm not really sure of the answer to that. I'm not a data expert. Trevor has been our expert really through this process. But as I say, the Modus fractional cover product has been quite satisfactory for our needs.
Okay, yeah, thank you, guys. Yeah, we have to let it go, and we're going to move to next talk. Thank you so much.
Okay, thank you.
Now use the microphone, but
Wait.
we need to. So just the.
Oh, sorry, Giles, I'm still online. We got a question from the app.
Sorry, was that another question for me?
Yes, we got another question for you in the app. It's guiding biomass. Sorry, I don't know what's said. In persistently eroded areas too. Can you understand this question?
I'm sorry, I'm just not, that the audio quality that I'm hearing is very poor. I couldn't understand that question.
Guiding biomass, re-veg, and persistently eroded areas too.
Oh, sorry, that's a lot clearer, yes. Sorry, is that question, are we capturing or monitoring what you just said?
Sorry, we don't have details. That's all we got from the app. Guiding biomass, re-veg, in persistently eroded areas too, from team over who?
Again, I'm not quite sure of the question. It's regarding persistent vegetation, native vegetation, that sort of thing. I know that Trevor has incorporated some base data about that in the modelling, so that we can certainly identify areas that aren't currently under long-term native vegetation and those sort of features as distinct from arable agricultural land. Yes.
Okay, thank you, Giles.
Okay.
Our next speaker is Helen Burns. She's from New South Wales Department of Primary Industries, and her research interest is in plant-soil interactions, mixed farming system. Let's welcome Helen Burns. Yeah, we will start in 1 minute.
Good afternoon, and on behalf of my colleagues, Drs. Jason Condon and Gwandi Lee, greetings from Wagga Wagga in southern New South Wales. Over the last few years, we've been investigating soil acidity in central and southern New South Wales and collaborating with land managers and their advisors to consider the effectiveness of acid soil management programs. I'm just going to give a bit of background to current acid soil management practices. Consider new management guidelines, soil sampling increments, new pH triggers and targets, and to suggest that we need to be looking more at monitoring soil pH to gauge the success of our acid soil management programs. Our current acid soil management programs are based on excellent work of the 80s, 90s and early 2000s. However, the guidelines developed then and the ones that persist were for outdated farming systems. It's time to update them. The focus has been and continues to be on ameliorating existing acid soil problems, so it tends to be a reactive approach, and often liming isn't initiated until there's evidence, clinical symptoms of acid soil toxicity symptoms, and it's driven by soil pH, the decisions, the liming decisions. And the soil pH values are usually derived from 0 to 10 centimetre soil samples. The trigger to apply lime is often when pH is at about 4.8 or below. That coincides with increasing levels of toxic exchangeable aluminium in the soil solution. And the tendency is to apply sufficient lime, only just enough lime to achieve pH target of between 5 and 5.2, at which level the concentration of toxic aluminium really starts to fall. And the lime rates applied are usually between about 2.5 tonnes per hectare. Reliming intervals tend to be about every 6 to 10 years, but vary depending on crop sequences. Now, in 2015-17, my colleague Mark Norton and I did some research looking at the pH profiles under acid-sensitive pulses in southern New South Wales. This was reported in the 2018 Soil Conference. But it's worth mentioning this because at that time, 0 to 10 centimetre samples really informed liming decisions and crop selection. And what we did was look at the pH in the 5 centimetre increments to a depth of 20 centimetres. And that showed up a very severe pH stratification. And to the extent that we had pH of less than 4.5 at least 45% of sites. So although the sites were earmarked for acid, or they were sown to acid-sensitive pulses, if the growers had been using 5 centimetre increments, they would not have chosen 45% of the paddocks at least. Now, most of these sites had a lime history, but were operating under minimum tillage systems, which tended to concentrate the lime in the surface layer. There wasn't a lime benefit reaching below to increase pH below 5 centimetres. Now, subsequently, my colleague Gwandi Lee has published a paper based on a long-term lime experiment that supports previous research that suggests that if subsurface acidity is to be ameliorated, then the pH of the 0 to 10 centimetre layer needs to be maintained at pH above 5.5. That provides sufficient alkali to neutralise acidity in the 0 to 10 centimetres and provides sufficient alkali to gradually move down the profile and improve pH below 10 centimetres. So we're advocating an increase in the pH target if subsoil acidity is an issue to pH of 5.5 and above. So more recently, we've been doing work in central and southern New South Wales, mixed farming zone, average annual rainfall of 500 to 900 millimetres. And we've been taking samples 2.5 to 5 centimetre intervals to a depth of 20 centimetres, just to look at the extent and severity of soil acidity in the region. Now, in the first instance, I have calculated the 0 to 10 centimetre pH at each of the sites based on the average of the 2.5 or 5 centimetre increments. And that has then been divided into 3 groups according to the pH criteria discussed previously. So we have group 1, the acidic group, pH less than or equal 4.8, 4.8 to 5.2, and then the third group, 0 to 10 centimetres pH above 5.2. Now, the 39% of the sites were in that problem acid soils group that should be prioritised for lime application. The mid-range group, 28% of sites, may or may not be prioritised for lime application. It's discretionary depending on the land manager's attitude to soil acidity and whether or not they're acid-sensitive species to be grown in the near future. The third group, 33% of sites. Now, these sites would have either been inherently higher in pH or would have received a recent application of lime to elevate the 0 to 10 centimetre pH. So from the 0 to 10 centimetre samples, this group would appear to have soil acidity under control. Now, when we consider liming decisions based on the 5 centimetre increment, that's going to give you a lot more information, the depth of the acidic layer and the severity of the acidity that the young plants are going to experience. It's going to inform liming practices and farming practices, such as species choice. It's going to inform the liming application method. Is lime incorporation needed to improve the depth penetration of the lime into the subsurface layers? And it's also going to inform lime rate and the frequency of lime required. Now, when we regroup the sites according to the pH of the 5 centimetre increments, there are 2 subsets that immediately fall out. Those with acidic subsurface layers, 87% of sites had pH of 4.8 or less in at least one layer between 5 to 20 centimetres. And the second group had pH above 5.2 in the 10 to 20 centimetre range. So that's within an acceptable range. You'd say that subsurface acidity wasn't an issue then at 13% of sites. Now, I have divided these further because when you look at the pH profiles, the liming programs would develop depending on the pH profiles in each of these groups. We've got 3 groups with acidic subsurface layers, 13% of sites, just 2 groups where the pH in the 0 to 10 centimetres is okay. I'll just look at those quickly. The most acidic group, 30% of sites have pH at 4.8 or less throughout the 0 to 20 centimetre layer. They should be prioritised for lime application. Second group, the pH profile is very similar to the soils from the 2015-17 survey, have had a recent application of lime, but as was the case with the survey sites, the amount of lime applied is not sufficient to have had significant impact on pH below 5 centimetres. So we've got acidic subsurface layers here. If managing subsurface acidity is the priority, then 78% of sites, those 104 sites, should be prioritised for lime application. That's compared with 39% when we considered pH of the 0 to 10 centimetres. Now, there's a third group with acidic subsurface layers. 9% of sites, the land managers have chosen to increase the lime rates to achieve that pH target of above 5.5 in the 0 to 10 centimetre layer. And that they have achieved a rapid increase in pH below 5 centimetres through incorporation. Now, this is a very good move towards improving subsurface pH, but these sites need to be monitored to ensure that the pH of the 0 to 10 centimetre is maintained above 5.5 and so the alkali moves down and improves pH in the subsurface layers. Now, when you look at the soils, the 2 groups, 13% of soils that have pH above 5, but below 10 centimetres, 13% of the soils were in this category. These soils tend to have high CEC, high buffering capacity, highly productive soils, which also follows they would likely have high acidification rates. These soils are going to continue to produce high yields and unlikely to show obvious symptoms of acid soil toxicity, even though this group, the pink triangles, is showing stratified pH and acidity starting to form in that 5 to 10 centimetre layer. We're concerned that these highly productive soils will fall through the cracks and they won't be picked up until we get severe acidification, in which case, at higher buffering capacity, high CEC, it's going to take considerable rates of lime to improve pH. We're suggesting these soils should be closely monitored for changes in pH, and we propose early intervention. So lime should be considered for this group here, the pink group, to ameliorate that acid layer at 5 to 10 centimetres. It's going to be a much more affordable and manageable option to alleviate subsurface acidity now. So that is a real warning, and please be sure that those sites aren't ignored in any acid soil management programs, soil testing programs. So just to summarise, the 5 centimetre samples identify the depth and severity of acidity, and they provide really good information to help formulate long-term liming strategies. The target pH, if you're aiming to ameliorate subsurface acidity, should be at 5 or above pH of 5.5. This increases the lime efficacy and enhances the downward movement of alkali into those subsurface layers. And please monitor any soils that you are targeting for acid soil management. It helps inform success and gives confidence to guide adjustments to liming rates or frequency or the need for incorporation. I'd like to thank the project partners, Holbrook Land Care Network, the Grassland Society of New South Wales, and acknowledge a funding support from the National Land Care Program. I'd also like to acknowledge the people who've been involved in developing or collecting soil samples. Thank you very much.
Thank you, Helen. We don't have any questions from the app, but I got a question. So are all your results dependent on the different soil types?
The soil types were very similar. Most of the soils you would consider to be chromosols. There were some dermasols and candisols, but the results that we're seeing, except for, I suppose the biggest variation would be the cation exchange capacity on some of those soils, but generally the acidification processes and the response to lime is considered to be similar for those soil types.
Okay, thank you. Yeah, so we just got last 1 minute. I just want to thank all our presenters. We learned cadmium isotopes, PFAS, eco-engineering, tailings, soil quality index, soil erosion risk monitoring, and soil management practices today in our session. So thank you all, and I look forward to meeting you all in person in the near future.